Let's take a few minutes now to look at arcs and chords in circles. And the first thing I'd like to show you is that if you have a random chord on a circle and you draw a radius that's dropped perpendicular to that chord, so that's a right angle, the chord is actually bisected. It's broken into two congruent parts. And here's why that happens. I'm going to add a couple of other segments, a radius here and a radius over here, to form two triangles. And those two triangles are actually congruent, and here's why. These two segments are congruent because they are radii of the same circle. The two triangles share that side, and then both triangles are right triangles. So therefore, by HL, these two triangles are congruent. And by extension, then, this segment is congruent to that segment, and we see that the chord has indeed been bisected. Now, the converse of this is also true. If we know that a chord has been bisected by a radius, then we know that the angles are right angles. So, written in words, what we've seen is a radius perpendicular to a chord bisects that chord. And the converse is also true. If we know that a radius bisects a chord, then it's perpendicular to that chord. The next idea I want to share with you involves two chords. So I'm going to draw these two chords, and I'm going to make them equally far from the center, equidistant from the center. So there they are, and if we were to measure this distance from the center to one chord, it's congruent to that distance to the other chord. And if that's true, these two chords turn out to have the same length. These two chords are congruent. And here's why that happens. To show you, I'm going to add a couple of segments. First, I'm going to draw this radius, and second, I'm going to draw that radius. And we know that these two radii are congruent, and we also know that this is a right angle and that's a right angle, and we also were given that this segment is congruent to that segment. So therefore, by HL, these two triangles are congruent, which means, by extension, CPCTC, that this segment is congruent to that segment. So therefore, we know that this piece is congruent to that piece, and we also know that the other half of each chord is the same length as its corresponding first half. So therefore, the entire chord here is congruent to the entire chord there. The converse of this statement is also true. If we know that two chords on a circle have the same length, then we know that they are equally far or equidistant to the center of the circle. Written in words, two chords that are equidistant from the center are congruent. The last idea I want to share with you involves two congruent chords. So I'm going to go ahead and draw two congruent chords here. One over there and one over here. And if these two chords are indeed congruent, what that means is that this arc, which is intercepted by one of the chords, is congruent to that arc, which is intercepted by the other chord. And here's why that's true. To show you it, I'm going to actually draw a few more radii on this picture. So there's one radius, here's another radius, here's a third radius, and then here's a fourth radius. And we know that all four of those radii are congruent, so I'm going to go ahead and mark them as all congruent. So therefore, by SSS, these two triangles are congruent. And then by extension, by CPCTC, we know that this central angle is congruent to that central angle. And if that's true, then this arc out here is congruent to that arc out here. So we've just shown that if you have two congruent chords, their intercepted arcs are also congruent. And we can express that in words this way. Congruent chords intercept congruent arcs. By the way, the converse of this sentence is also true. If we know that we have congruent arcs, then their corresponding chords are also congruent.